under conditions where autophagy is deficient in the nervous system or the whole fly, on the interactions with TOR signaling and changes in fly behavior. The next presenter is one who I have had the honor of growing up with. She has been a role model to all the ASR students, and her passion and commitment to always improve and get better in this program is mesmerizing. Over the past 2 summers, she has dedicated hundreds of hours at Mount Sinai Icahn School of Medicine under the mentorship of Dr. Timothy Blenkinsop. This past summer, she completed her research project entitled Mitochondrial Replacement Therapy in Degenerative Retinal Pigment Epithelial Cells. Throughout her ASR experience, she has been named a Neuroscience Research Prize finalist, South Asian Americans Women's Alliance finalist, received 2nd place at the Long Island Science and Engineering Fair, and highest honors at the Long Island Science Congress. In addition, she received a research report badge and was named a Regeneron semifinalist. Next year, she plans to attend Stony Brook University, where she will be majoring in biology. We are also proud of her accomplishments and look forward to hearing about all her future success. It is my sincere pleasure to introduce my older sister, Jennifer Rakimov.
Thank you, Laura. Hello, my name is Jennifer Rakimov. 8 years after my grandmother's liver transplant, we learned that she needed another new liver. Sadly, my grandmother passed away while her name was still on the organ donor list. It was at this moment that I realized I wanted to study regenerative biology. My research project is entitled Mitochondrial Replacement Therapy in Degenerative Retinal Pigment Epithelial Cells. In the United States, approximately 11 million people suffer from age-related macular degeneration, which is the leading cause of severe visual impairment in our elderly population. It is characterized by a progressive degeneration of the retinal pigment epithelium. The RPE is a monolayer of cells that perform highly specialized functions essential for the homeostasis of the neuroretina. This monolayer is located in the macular region of the eye, underlying the photoreceptor cells and overlying the choroid membrane. Each RPE cell supports 30 to 50 photoreceptor cells by providing them with nutrients, getting rid of their waste, and phagocytosing their superficial segments. As you age, degeneration of the photoreceptor cells results from the dysfunction of RPE cells due to a lack in energy. The mitochondria produce approximately 90% of the essential energy necessary for cellular function. Aging and neurodegenerative diseases in the retinal pigment epithelium are linked to impairment of mitochondria and its decline in ATP production. This results in age-related visual dysfunctions such as age-related macular degeneration. This led me to hypothesize that if degenerated RPE cells are treated with young human embryonic stem cells mitochondria, then RPE cell cellular function will be restored. In this experiment, 2 cell cultures were used, RPE cells and human embryonic stem cells. The mitochondria were isolated from human embryonic stem cells using a mitochondria isolation kit, which involved several cellular fractionations. Then, these mitochondria were stained with mitotracker fluorescence probe green and TOM40 red, which was then complemented with secondary antibody 546 rabbit red. Our mitochondria were then co-cultured with RPE cells. You can see that the first cell shows a regular RPE cell that has not been modified. Then we would add our mitochondria on top of these RPE cells and leave them for overnight incubation, in which our mitochondria would phagocytose into our RPE cells. An additional experiment was conducted, the mitochondria depletion experiment, in which we depleted these RPE cells of their already present mitochondria, and then we phagocytosed our mitochondria inside and conducted several assays to see if cellular function was restored or even improved. Figure 4 shows the isolated mitochondria at 2 different magnifications, they were mitotracker fluorescence probe green, TOM40 red, and an emerged image is an overlapped image that shows pure mitochondria being isolated and pure mitochondria being viewed under the microscope, no other organelles. The MFG phagocytosing supplement was used during the phagocytosis experiment. When MFG was not present, you could see that there was barely any mitochondrial attachment to the RPE cells. However, when MFG was present, there was an abundance of mitochondrial attachment, clarifying that it is essential to use MFG8 in all our phagocytosing experiments. Afterwards, I hypothesized that if I would add more mitochondria to my RPE cells, then there would be a greater energy production at the long run. However, what I learned was only a 1-to-1 ratio, meaning the number of human embryonic stem cells used for the isolation of mitochondria to the number of RPE cells was the most efficient. Since I was working with a disease, age-related macular degeneration, I had to mimic this disease into our healthy RPE cells. So in order to do this, I treated them with concentrations of ethylene bromide. The control in this experiment would be a regular person's vision in which no aging has occurred. Then the 0.025 microliters of ethylene bromide would be the smallest concentration of ATBR, and it would be the early stage of AMD. Then mid-stage of AMD, and the latest stage of AMD, which would be close to blindness. You can see all the cellular apoptosis that occurred around the cells. We phagocytosed our mitochondria into the cells, and then conducted a trans-epithelial electrical resistance assay. Since I was working with an epithelial monolayer, their TR, their cellular tight junction, is very strong. So before treatment, their TR scale was around 300. Then after 1 week of treating these RPE cells with concentrations of ethylene bromide, depending on the concentration, their TR scale would decrease. So the higher the concentration, the lower the TR scale. Afterwards, I treated my RPE cells with our mitochondria, and you can see that their cellular tight junction improved significantly. However, the cells that received the highest concentration of ethylene bromide, 2.5 microliters of ethylene bromide, which would be closest to blindness, ended up undergoing cellular apoptosis. This indicates that it is essential to treat AMD at earlier stage and do not wait till the last minute. In conclusion, this study shows that RPE cells are able to phagocytose human embryonic stem cells mitochondria, and mitochondrial replacement therapy does improve cellular function in RPE cells depleted of their own mitochondria. These new and improved RPE cells could provide a potential solution to vision loss and end the days of glasses and contacts. During the summer of 2017, I plan to return to the lab and repeat all my experiments. Additionally, I would like to conduct an in vivo study on AMD rabbit models and hopefully have my research published. I would like to thank my mentor, Dr. Timothy Blenkinsop, my teacher, Ms. Barbie Frank, and my family for all their help and support. Here are my references. Thank you very much.
Hello, my name is Claudia Dreyer, and I'm a sophomore